Thank you very much, John.
Thank you.
Ramin, can take one quick question for John, if there is one. Otherwise, we'll move on to a brief general discussion.
Thanks, John. Thanks, Matt. I don't see any specific questions from attendees, so maybe it's good to move on to panel discussion. And if there are any questions that come up, then they could be raised during the panel discussion. How does that sound?
Great, thank you. Yeah, so I appreciate we've run over. So thanks to the 134 people who are persevering as we go past 4:30. We will finish by 4:45, but I would like us to have a brief panel discussion before we go. So I've pulled out some of the questions that have been coming through and some from before the events. And the first one I want to put to everybody is it's from Barbara Dickinson, who asks, given that we generally only use causal methods to estimate average causal effects, how can we use counterfactual prediction to reason at an individual level? Specifically, talking about the development of counterfactual prediction models using trajectories generated under a hypothetical policy, for example, using G methods. Does this not require generation of individual patient outcomes? Would anyone like to jump in on that? It's on your street, Carla.
I think I tried to answer that in the written form already. So what I said there is that indeed sort of methods like G computation as a half step towards answering the average treatment effects, they do have to give you predictions for the two potential outcomes, but that's not to say that you can then use those predictions of potential outcomes and run with them as if they were counterfactual predictions, because those models were not created for that purpose. So they're only what we would call a nuisance, a nuisance model. So they're good enough for average treatment effects, but they're not good enough for counterfactual prediction. I would say, because you're only using them to get to the correct contrast, but not to do any inference on the predictions themselves. So that's what I said.
I have a view on this, which is that this is sort of hitting on an epistemological limitation of statistics and its interaction with the world and the questions that we're actually interested in. So clearly the fundamental problem of causal inference says that we can never know what's going to happen for an individual. And so the idea of creating individual level estimates is itself a stretch. What we're really doing is sort of creating some kind of average that would apply to a group of people who looked like that. And then we're trying to use that information to instruct what's best for this individual. But ultimately, everything that we do in statistics, everything we do in data science, machine learning, etc., is really strictly about groups, and we're stretching that to, in a way that we only get these funny probabilities, and there are then all the questions of how do you actually interpret a probability of 60%, let's say, when we're trying to make one-to-one decisions for individual people.
Thanks. So another theme that came out in discussion was, I suppose, around the issue of transportability. So a few questions in one here that I've sort of collected. So one is around, I think it was me that said that causal factors probably transport better to different populations. And somebody else asked, how should we check for or account for differences between the data sets when we move from an internal to an external data sets? And then somebody else asked, relatedly again, why do we see much better performance on internal validation than external validation? Ramin, I wonder if you want to pick something up on those.
Sure. I think to jump on the second point first, I think Carla made quite some statements on this already, some explanation regarding, you know, the shift that we see. I heard this in another talk, so drift that can happen. I think this was a comment from one of the, actually someone who left a comment here, one of the question and answer comments, that over time we tend to notice there are changes that occur in a system that we then need to occur for. So I think that's natural that we tend to see a drop in performance, and that's perhaps where maybe there is some at least logic in terms of a formal, I saw one of the questions there, mathematical proof for the idea that causal factors are likely to, you know, better transport across populations. That I don't know for sure. I would be fascinated to know more about this. If there's anyone that has any comments on this or any evidence for this, I'd really like to see this. I know there are schools of thought and that really for prediction, it's not necessary. Of course, it's not necessary to model in for pure prediction causality, but I do wonder, you know, if something has absolutely no distant or through somewhere within a causal structure, I wonder how is it so predictive if it is a strong predictor? What examples do we have where there's absolutely no, whether it's a common ancestor or parent or somewhere within a larger causal structure, how can it be such a great predictor if it's not part of that system? I'm curious anyway, if others have comments.
There's some interesting examples. You've seen some more generic machine learning applications. So you know, for example, that Atari video game player from DeepMind that plays video games based on the video feed. If you change the color of the video feed, it does terribly. Even because color actually helps a lot in predicting actions, but it's not a very stable feature, even though it's a good predictor on how the environment is reacting to what you're doing. Just a small example that, of course, is not a very realistic setup, but does illustrate a few things. I mean, you can even think in terms of instrumental values in intention to treat, right? That if you think that just a policy that assigns whether somebody gets nudged to take a treatment is not as good as assessing, as knowing that a person took that treatment or not. Even though for policy making might be a good thing to evaluate whether particular nudges are good, it doesn't tell you much if you move this to a new country, for example, where people respond differently to that incentive, but the biological mechanism, how disease is related to your treatments would remain stable, you'd think of, or more stable at least.
Yeah, that does make sense. It kind of resonates with, so going back to the Caruana example, so some commentators say Sushi Saria, for example, he mentions that this characteristic of asthmatic patients being highly associated with being put in the ICU is a non-stable characteristic of the problem we're trying to study, and therefore it doesn't transport very well. It results on covariate shift. And so if we know or strongly suspect that there is certain characteristics that are non-stable, as Ricardo was calling them, or that create covariate shift, as I would call them, I think this needs to be taken into consideration very, very thoughtfully to sort of help first with getting correct counterfactual predictions for those that we don't actually observe, but also to improve the external validity, I guess, of our predictions.
Yeah, I would just agree that theoretically, if it's a good predictor, you'd imagine that it would be involved in some kind of causal process. But that clearly it's this distinction between how localized that is and how generalizable that is. So there are some fantastic examples of machine learning algorithms learning some kind of hilariously local features, like the classic cat-dog identification task, where, or even an animal identification task, where actually they learn, is there a blurry background? Because these are the kind of photos we take of our pets, whereas that was actually just because that's what it was trained on. Whereas if we were teaching it features like whiskers and and ears, then that would be much more relatable. So it has something to do with the consistency, the transportability, and our sense of how common those mechanisms are versus how localized they are to whichever context we're first working in.
Thank you. I think we're going to have to leave it. There's loads more questions, but in the interest of time, we're going to have to. Thank you for joining us. Really overwhelmed by the interest in this event. Absolutely fantastic. So many of you were able to join. I hope you've enjoyed it as much as we enjoyed the fortnight in putting this event together. Please do reach out to us if you have ideas or would like to collaborate on anything we've talked about. As I say, it's all work in progress, and I think we're all really keen to take these ideas forward and bring other people on board that are interested. So please do reach out to us. There's been lots of questions about the availability of the slides and the event, so that this has been recorded and it will be on YouTube after the event, and the slides will be shared as well. There'll be an email sent out to people on Eventbrite telling you where to get the slides, or just message one of us on Twitter or email us if you snuck in without being registered on Eventbrite. On that note, I'd like to conclude the session. Thanks to Turing, and particularly to Ioannis and Jesse and Charlie and the team that have taken care of the subtitling throughout the afternoon. That's been really impressive. I've been amazed watching how accurate that was. So thanks very much to everyone. This is just the beginning of a journey to address some of the things that we raised today. So thanks very much and goodbye.